our galaxy group. Please entire blame is on me. I have had a lot of support for the slides and so from Grazia Umana, who is one of the chairs. I'm an infrared astronomer, so this is new territory for me. This is the Our Galaxy group of the SKA, so the name says everything. So you say, oh, this is boring again, the Milky Way. We've had that for hundreds of years. Well, I think it's very nice summarized there's a review paper on the Milky Way by Bland Hawthorne and Gerhardt. And they really say that the Milky Way is a benchmark for understanding this galaxy, and it's the only galaxy where we can really make high angular resolution observations and probe everything in detail. There's also this other fancy expression that is called near-field cosmology. I mean, it means nothing else than our entire astrophysical understanding, almost all of it, not all of it, is based on the Milky Way. So it's really the fundament of everything. And the SKA will provide us with the most complete and most sensitive radio catalog of the galaxy to date. And this is a complete game changer. That was the short version. So now I'm trying to elaborate a bit more in detail. There's an overlap, of course, with all the other working groups. So our galaxy, it's not a science topic, it's an object. So there's a strong overlap, but I think it makes a lot of sense to foment this kind of issue, this kind of container of the galaxy to focus the observations and make efficient use of the instrument. So the big picture, of course, is, as always, as most of astrophysics is concerned with the cycle of matter, of baryonic matter in that case. Throughout galaxies, you have gas that accretes atomic gas, you have molecular gas, you form stars, you change the chemical composition, you expulse it again, you start the entire cycle again, but you also end up with some remnants. And all of these stages can be probed with radio observations. Of course, you can probe the molecules, you can probe stars with the SKA, you will even be able to probe just normal stars in significant numbers. We will learn a lot about stellar remnants and about supernovae remnants, about this entire cycle. Our entire knowledge of this cycle will be put on a completely new pair of shoes or new pair of feet even. In this case. This is the Galaxy Working Group. Of course, there's continual evolution, so this may neither be complete. Some people may be there in and out, so Mark Thompson and Grazia Umana as chairs. There's a very broad coverage of nationalities and of expertise, and many of them are parts of precursors. So the gist of it in the end would be try to promote surveys of the galaxy with the SKA. Maybe I don't dare to use that because I'm new in the political game, so I don't know if anybody kills me if I mention the word key science project. But for example, make a galactic plane survey, which would take a few thousand hours and give us the most sensitive high angular resolution view of the galaxy in radio up to date. Galactic plane makes probably sense because you wouldn't want to make an all-sky survey for the galaxy because, I mean, it's our galaxy, so most of the stuff is really found in the plane. There's a lot of commensality with other projects or working groups, in particular magnetism pulsars and the so-called Cradle of Life working group. So there's a big overlap, only that in this case it would all be focused on our galaxy. The impact, of course, would be that you could study massive star formation in all its stages from the protonuclear cores up to the latest stages of gas expulsion, stellar winds. Radio stars, it's a fancy word that I always stumble across. Radio star, as far as I understand it, it's just a star that is detected at radio wavelengths, which can be any star if you're sensitive enough. But in this case, the interesting thing is you not only get pre-main sequence stars from accretion, from jets, but you also can get main sequence stars. Within a few parsecs, you can even probe stars like our sun. And then, of course, evolved stars that start ejecting matter that have ionized gas around them. They're ideal targets for radio observations. Then there's interstellar medium, circumstellar medium, H2 regions from ultra-compact to giant. You see them all across the Milky Way. You probe outflows, supernovae remnants, planetary nebula, all across the galaxies. Stellar remnants is very important because you will be extremely sensitive to any kind of accreting stellar remnants, usually in binaries, but turns out if it's nearby, you can even find isolated black holes, for example. And then, of course, I think we should not, Phil Diamond said that already, we should not neglect the unknown, or even the unknown unknowns, as I like this expression, serendipitous discoveries. And as always, since the Milky Way is where you are most sensitive, that's also where you would expect a lot of these serendipitous discoveries to happen. So I've said that already, it will be the most complete catalog of radio sources in the Milky Way we ever have. And of course that means we go from very small samples to really statistically examining everything. It being the Milky Way, there's another huge advantage. We have a lot of multi-wavelength information, so there's this fancy word of multi-messenger astrophysics, very fashionable, and you can really work on that. You have all kinds of optical and infrared surveys, you have X-ray surveys, so you really can go across the entire plate and have the full menu of electromagnetic radiation to study your objects in a statistically meaningful way. So this is not just a survey in one wavelength. Once you have SKA and you add everything else, you have it all. Now, after this overview, which, I mean, this is the main case, let's drive home some science cases. Just, there's not much time, so I'll just give you a few appetizer, a few tapas. They're free. Accreting objects. So this is a nice graph that I stole from somebody's presentation. It shows you a bit kind of, this is Eddington luminosity, bolometric luminosity, and this is radioluminosity, and it shows you a bit where you could go with a galactic plane survey with the SKA. There's always the issue of the exact sensitivity of the SKA. These numbers dance up and down, but I mean, typically within a factor of 2, you can be fairly confident. So this is all logarithmic, so this is very nice, so it wouldn't change too much. And as you can see, out here we are 10 kiloparsecs. That's basically beyond the galactic center, and there you basically catch all hard state black hole binaries. So the hard state is basically when accretion is very low, you have a jet there, but you don't have a big accretion disk, for example. You have a fluffy accretion flow, and that's actually quite interesting regime because we don't know much. We kind of have a relatively solid understanding of accretion in the thin disk regime, Sakura-Sonyaev solutions, but in these fluffy accretion flows, like they happen also at the center of the galaxy around ZJ star, we really don't understand too much. So it would be good. You have statistically, you suddenly have hundreds of thousands of these objects. But it's interesting. So there's this isolated black hole thing, and when I first saw this, it drew my attention out to maybe a few hundred parsecs. You may even be able to see isolated black holes. So that's quite interesting. It's the first time that you can see them. Here's your impact, I've mentioned already. It's study of accretion, study of outflows, ejection mechanisms, and of course the evolution of binaries and the number of compact objects in different regions of the Milky Way. So radio stars, again, a radio star is nothing fancy, it just means radio detected star. I think the detected is being omitted for briefness. This is a nice Hertzsprung-Russell diagram. I apologize, I'm quite sure you cannot see it nicely at the back. Because of the light here. This is just a color, so we have blue to the left, O, B, A, F, G, K, M type stars, and this is the magnitude. So of course up here you have to the left up, you have all the massive stuff, massive main sequence stuff, O and B stars. You have here the main sequence, then you evolve off the main sequence and towards the giant branch, and you see stars everywhere, although few of them are main sequence. So the main sequence is just the OB stuff, and when you hear solar mass stars, there's lots of these yellowish dots are T Tauri stars, for example. They have outflow, so that's non-thermal radio emission, and then when you go to evolved stars, red giant stars, you also see again a lot of them. But this is from 2002, it's just 440 stars. I don't think it has changed fundamentally, this picture. Maybe we're at 500 now, but in order to fundamentally change that, you need the SKA. So what kind of radio emission do you have? Just to make a brief, very brief dip into physics here, or not even a dip, it's just sticking our feet into the water. So you either have, for bright radio stars, you either have a very big emitting surface and thermal radiation, and examples of this is everything from H2 regions over OB stars, planetary nebulae, atmospheres of normal stars if they're very close nearby, and then of course stellar winds. And the other thing where you can go in radio is of course non-thermal emission, synchrotron, gyrosynchrotron radiation. And this is of course everything that accretes or has jets, flares, magnetospheres. That's where you go. So interesting is again, you could really, in a statistically meaningful manner in our galaxy, you can cover everything from stellar birth to death with the SKA. So again, the current state of the art is we're really limited in sensitivity. There's very few stars we can discover, except if they're exceptionally bright or exceptionally nearby. And the other problem is selection bias. Since it's so expensive to discover these things and you need hours of observations at major interferometers, in the end, you only target them when you already are pretty sure you detect something and have a very solid and very specific astrophysical case. Now, with the SKA, you will have a complete paradigm change. You will have real population studies across the entire galaxy, statistically meaningful and fairly complete samples. Basically, probably throughout the Milky Way, but at least within several kiloparsecs. Also, you don't have to worry about extinction, which is quite nice. And then you could do things like study the radio properties of these sources versus their mass, versus their chemistry, versus their rotation, so you can really dive into stellar physics there. This is a detection forecast. Again, here you have distance down here now, so 1 kiloparsec, 10, and 100 to the right, for those who don't see it. So in the middle we're 1 kiloparsec, here we're at 100 logarithmic scale. And again here a logarithmic scale of radio sensitivity. Again, the numbers, these lines, they may dance up and down, but this is SKA1, mid 10-minute integration time, so you basically see out to 10 kiloparsecs, or even out to 100, you see all Wolf-Rayet stars, for example, in the galaxy. You will detect them all. You will finally have a complete sample of Wolf-Rayet stars. And then if you want to, for example, on the other extreme, have a sun-quiet star, well, that's just within a very few parsecs, so it's just within a few parsecs. But nevertheless, you can detect these things. So my pet object is the galactic center. I'm there, I'm an infrared astronomer. It's very special because it's so nearby, and it's the only galaxy nucleus we can study. This is the Andromeda seen with the Hubble Space Telescope on the same angular scale, same field of view. This is the Milky Way. So instead of a blurb, you see thousands of stars. And I think that drives home the message that there's nothing that we can ever do in another galaxy that will rival what we are doing in the center of our Milky Way. And it's a very special environment for all of astrophysics. It's the densest stellar structures in the Milky Way. I mean, you reach up to 10 million times the mean density of stars compared to the solar neighborhood. So you move between 10 to the 5 and 10 to the 7 stars per cubic parsec there. You have a massive black hole that influences the interstellar medium and the stars. It's currently, or it has been in the very recent past, the most prolific massive star-forming region in the entire galaxy. It's a high metallicity environment, so you have about twice solar metallicity in the galactic center, which is interesting because this is a regime where we cannot calibrate our models well, because so far there's no large-scale environments, but in the galaxy, the center of the galaxy, we know for 1, 2, 3 years now we really have this high metallicity environment, which also means there will be very strong stellar winds, which also means it's easy to detect these things in radio. The international mass function may be different. You have 10% of the Milky Way's molecular gas there. You have a magnetic field that is 10 or probably even 100 times stronger than in the rest of the galaxy. So whenever you want to do studies in nature, you go to extreme regions to probe your theories. And this is an extreme region where you can do fundamental astronomy, astrophysics of massive black holes, of stellar remnants, of star formation, of massive star formation. There's also lots of multi-wavelength synergy. You have lots of data from X-ray. I myself am leading the first high angular resolution large-scale survey of the Milky Way in the infrared. So we will, and we may even have proper motions in 5 years when the SKA starts to work for about 3 million stars. And then we can really relate these objects to each other. You see plenty, so these are precursor studies from Farhad Yousefzadeh, for example, with the VLA, with the JVLA. This is Sagittarius star. This is just very small angular scale, just 10 by 10 arc seconds. And all these dots here are radio-detected stars. In this case, they're massive young stars. We're also working, so Teresa Gallego, a student of mine, she's working on a study of the ARCHES cluster. The ARCHES is one of the most massive young clusters in the entire Milky Way, 150 OB stars. This is an infrared image from Hubble, and here you see some detected stars with the JVLA. Another appetizer, this is from Sarao, from Meerkat. So this is a first shot they took at the galaxy, at the center of the galaxy at 750 megahertz. It is mind-blowing if you compare that from the last similar work, which was at the end of the 90s, from Ted La Rosa et al. For me, myself, it's still a bit low angular resolution. I think they're right at 15 arc seconds or something like that. So I'm more interested in the stars and stellar remnants. So finally, time expired, I'm being told. So just very quickly, other sciences would be time variability in massive clusters and young clusters to study what happens to the stars there, to YSOs, why do they flare? It's a strong relation to cradle of life, and also for stars, planets, and civilization. That's also something you would do in the Milky Way. Study magnetic fields of stars, how they interact with planetary atmospheres, how do planetary magnetic fields interact with other stars. I don't think we will detect civilization in our galaxy because we're more focused on surveys. If you want to detect a civilization, I think you have to drill much deeper with a dedicated program. So this is it. Thank you very much.
Okay, very nice. Questions? Yes, please.
Researches by using the data from other people.
Okay, that's cool.
For that, they need to basically build up their own hardware. And that's something that
I did not know that, but that strengthens the case for a galactic plane survey considerably, because that's where you would first look, I think. Yeah. Okay, thank you, Ithaskun. I prefer comments to questions. I may not have the answers to your questions.
I have a question.
Oh.
Well, it's a simple one, I think. It's just, could you mention some of the our galaxy physics that can be made with the first phase of SKA? What is the first science that you think can be reached with the first phase, SKA1, and what about the second?
So take it with a pinch of salt, man. I'm not a radio astronomer. But of course, as you see, we're completely ignorant on radio stars, for example. And I think radio stars will be impacted immediately from phase 1. So there's no doubt that you will immediately multiply by 10 the number of stars that you have in a Hertzsprung-Russell diagram for the galaxy. Okay, I pulled this number out of the air, but I'm pretty sure to bet a few beers on, or champagnes on that number. So, and the other thing, I think the entire field of compact remnants, for example, binaries, black hole binaries will also have a very strong SKA, also in the very first phases will already have a strong repercussion in that, I think. Of course, the next thing is pulsars. I mean, pulsar people, they are just burning and waiting until the SKA is coming. So.
Yes.
I can make a quick comment on pulsars as well. So the SKA, in principle, should be able to detect every single pulsar beam towards the Earth in the galaxy, and this means all the line of sights to also extract properties of the interstellar medium on all these line of sights. In its first phase, no. In its first phase, it's still, but okay, first phase is still will be a huge step forward. But eventually, we should be able to detect every single pulsar. Of course, it's the best way to try to detect as well pulsars around black holes, which is something we are aiming for since a very long time for gravity tests, etc. So.
If not, let's thanks again the speaker. And So the next talk is by Diego Ranz from Instituto de Física de Cantabria, and it's on cosmology and the epoch of ionization with the SKA.
So good morning, everybody. I'm going mostly on behalf of the group of people, large group of people who work for the Spanish White Book on the SKA. In particular, for the group who wrote the chapters about cosmology. Well, the big questions we have in cosmology are big questions with capital B. What is the nature of the primordial density fluctuations of the universe? Which is driving the acceleration of the universe? It is true that the cosmological principle holds, that it's the universe isotropic and homogeneous. How about general relativity? Do we need modified gravity? And many other questions. In this slide, I've marked in red the questions that are a priority for the first phase of SKA, but at the end, we will plan to address all of these questions. What do we need for that? We need huge volumes of the universe observed, if possible, with high resolution, and if not, at least with high sensitivity. And to follow all this evolution around the evolution of the universe. So let me just remind a little bit about the history of the universe, starting from the early universe that is probed with particle physics, mainly, and the CMB. And on the other hand, we have the modern universe, the universe we see now, the local universe, and in the middle is this gap, okay? What we call the cosmic dawn and the dark ages. The present-day telescopes arrive more or less to hit around 8, 10, and with SKA and other facilities, like for example the ELT and the James Webb Telescope, we plan to arrive around 30, even 50. And the science fiction future, we will have these moon-based interferometers. And in this gap, we plan to fill. There is a lot of stuff, interesting stuff happening. Basically, the formation of the first stars, the first galaxies, the evolution, the nonlinear evolution of structure, and the transition between the matter-dominated universe and the dark energy-dominated universe. Of course, we cannot rely on visible light to arrive to these dark ages, so we need another probe, in this case, H1, the 21 centimeter. This is the basic equation that is giving you the brightness temperature of 21 centimeter line. And here you can divide three different contributions. One of them is the local physics, the medium, and the relation between this temperature and the temperature of the background radiation, namely the cosmic microwave background. Of course, the density fluctuations we want to map, and dependence on the cosmology, mainly the baryonic density parameter, the mass density parameter, H parameter. And of course, a last term, depending on the velocity, the proper velocities of the fluctuations. So this weak signal is going to be a wonderful probe for the physics of the intergalactic medium. More physics. You check how this signal is going to be around the cosmic evolution of the universe. During the dark ages, you would observe the 21 centimeter line as an absorption line. The CMB is brighter than the dust at this epoch, so you will observe absorption line. And nearby the cosmic dawn, this absorption decreases or increases in intensity. Then you get positive bump here, and then when you obtain the final reionization of the universe, the signal becomes very, very small. So we have this wonderful facility we have this SKA, which is going to be a game changer. And we plan to make, we use 3 different kind of operation modes. I'm going to talk about, just very quickly, about the differences between these 3 things. But the important thing is that all the surveys we are going to carry out are going to be commensal. I mean, all of them are designed to be useful for everybody, for all science cases, and to have a great communication between them. So you should not consider these 3 different observation modes as separate items, but as to things that communicate. For example, you can obtain redsheets from here and benefit with these redsheets the observations in intensity mapping or in continuum. So let's start with intensity mapping. There are so many science cases here, so what I'm going to tell is just a quick list of many things we can do, and then I will select almost randomly just 1 or 2 examples just to give you in this short time. Okay, what is intensity mapping? Intensity mapping is basically the analogous to CMB observations, but in tomography. Instead of following individual objects, we are going to integrate the 21 centimeter intensity in big pixels and to obtain fluctuation maps, very similar to the CMB, but again, not only located at 400,000 years after the CMB, the Big Bang, sorry, but following all these fluctuations across cosmic history. So we will have a large volume of these fluctuations, and we can do the same kind of analysis we do with the CMB, but in 3 dimensions. We can have not only angular power spectrum, but also 3-dimensional power spectrum. And you can do exactly the same kind of things you do with CMB maps. You can check for non-Gaussianity, you can check for statistical irregularities, you can calculate power spectrums, etc. So, among the many science cases you can address with intensity mapping are, apart from the power spectrum, baryonic acoustic oscillations, redshift space distortions, physics on extremely large scales, test of the curvature of the universe, primordial non-Gaussianity, lensing, and neutrino masses. Among all of these examples, I'm just going to mention very quickly Bayes and neutrino masses. For baryonic acoustic oscillations, well, we can do it with intensity mapping, and we can do it also with galaxy surveys. So this slide could be also in the other section of this talk. But well, just considering just intensity mapping, that I forgot to mention is the easiest mode of observation. We can have, just using SKA1, similar results to Euclid. So it's going to be competitive, not only competitive, but complementary to Euclid and many other experiments. And with SKA2, we will have even lower error bars. And the important thing with Bayes in the case of SKA is that we can not only, normally these baryonic acoustic oscillations, the selection function of galaxies we are using to study it is centered around redshift 0.5 to 1. With SKA, we are going to widen this interval. So we are going to be able to map these acoustic oscillations between redshift 0.0 whatever and redshift 2 or 3. So it's going to be a more dynamic image of this standard ruler. More things. Neutrinos, another example, among many other examples. You know, we can try to weight the mass of neutrinos, because neutrinos, when they are flowing across matter, if they have mass, they can affect the power spectrum of the mass distribution. So in this plot, you can see how combining Planck, for example, CMB, this is the contour for mass of neutrinos with respect to the sigma 8 parameter, just using SKA, which is going to have different systematics and different degeneration space, you can narrow a lot the mass of the neutrino and also the sigma 8 parameter. So this is going to be one of the things we can do with density mapping. Let's move to a radio continuum survey. This is similar to other many radio surveys made in the past, in the sense you detect galaxies, you make a survey in radio. And in the past, radio surveys alone has been a limited utility, because normally radio continuum is dominated by synchrotron. Synchrotron has a very self-similar spectrum, and it is very difficult to get redshift information with radio continuum surveys. But on the other hand, the synchrotron is dominating the star-forming galaxies at low redshift. So it is important to get that. In the past, radio continuum surveys were small and not competitive with optical surveys in the sense of cosmology. But the goal here is to rival, optical surveys. For that, we need to get enough sample, so a very big number of galaxies. Which is going to be the main advantage with respect to optical surveys? A huge area. SKA is going to observe between 25,000 and 30,000 square degrees. It's going to be the largest survey. And different systematics with respect to optical surveys. For example, synchrotron is not obscured by dust. So we are going to be able to see star-forming galaxies not obscured by the dust that is blocking this signal. And the K correction for synchrotron is very simple. So the systematics is going to be more controllable. What is the main problem? As I mentioned before, this synchrotron spectrum makes it very difficult to obtain photometric redshifts. And in radio, we have no or very little emission lines apart from the 21 centimeter line. So obtaining redshift information is going to be very difficult. But there are some works indicating that using only a small amount of redshift information from other plans, even inside SKA, for example, using the 21 centimeter line survey, we can break a little bit this problem with redshift and obtain not very accurate, but enough photometric precision in the redshift to make cosmology. So what can we do? Well, before doing that, which is the number of sources we plan to get? Well, with a sensitivity of 1 microjansky, which is going to be obtained in 10,000 hours, we will have like 10 to the 8 sources for SK1, 10 to the 9 for SK2. That is going to be orders of magnitude larger than present surveys. Well, again, we have many science projects. This is, for example, just to show forecast of the number of galaxy clusters we are going to find with SKA compared to Rosita and to Euclid. So we are going to be, basically we are going to duplicate or almost multiply by 4 the volume that is going to be reached by Euclid. So we can, for example, make studies of isotropy and primordial non-Gaussianity, and using some limited information on morphology of the galaxies we will observe, just a quick and dirty distinction between different kinds of galaxies, we are going to be able to constrain the FNL parameter to a level that is more or less half the current level obtained by Planck. This is the curves. This is the Planck 2013 limit, Planck 2015. Here there is no the Planck 2018, but I think it's more or less similar like that. This is going to be Euclid. CMB experiments are limited in some sense. Even if you go to a lower detection limit, you can you reach some plateau. But using SKA, you can arrive to lower limits in sigma FNL. And finally, I have, okay, my time has expired, I'm sorry. Well, finally, the 21 centimeter survey is exactly the same, but using the emission line just to get the redshift. This is a kind of peridiogram. Here you have frequency, here you have position, and you will find this kind of blobs that are galaxies. And then you can get a huge catalog of galaxies up to redshift 2, and to study many other things, like, for example, redshift space distortions, dark energy, modified gravity, cross correlations with other larger scale structures, and wherever, just to give you a tapa, as said. These contour plots are constraints on dark energy, forecast constraint energy for using acoustic baryon oscillations. And here you can see this is the contour plot expected by for Euclid. For SK1, we will not be competitive, but with SK2, we will be pretty competitive. And this, for example, another important thing is related to how to constrain redshift space distortions as a function of redshift. This is the inverse of the signal to noise, so basically a low curve here indicates you have a high signal to noise detection. And okay, you will think, well, more or less you are going to have the same things you have with Euclid. Not exactly. The problem is that with Euclid, you are limited to high redshift galaxies. But with SK, we are going to have all of them. Low redshift galaxies that are going to be measured with SK1, and high redshift galaxies with SK2. So it's more complementary. So just to finish, saying that, okay, this SK is going to be the panacea for cosmology. The high precision cosmology is going to be high resolution cosmology, precision cosmology with SKA. And the key word here is commensality and sharing data. Always, if we can solve the problems ahead of systematics, data analysis, at wherever. Thank you.
Thank you. Questions? So, I don't know if there is no question. Could you mention a bit about the epoch of reionization? Because you mentioned many useful probes for cosmology. But
It's a paradox because I am in the epoch of reionization group, but I'm also a cosmologist. So, well, yeah, the main idea is for epoch of reionization is to see this transition. Around here, okay. It's a difficult part because here you get exactly this 0 point. So it is going to be difficult. And for a moment, the main, as far as I know, the main tool here is going to be intensity mapping. The idea is going to be just how the power spectrum of the fluctuations evolves, and how these hydrogen regions disappear during the reionization. So, well, I cannot comment because I'm not an expert.
Do you know if there are any pilot surveys or pilot projects to demonstrate the technique of intensity mapping?
Yes. Already working. LOFAR is doing intensity mapping. Paper is doing intensity mapping, and also I think the precursors, I mean Meerkat, are already doing that, because it's basically the easiest technique. Easiest. yeah, it's already working. There are published works on intensity mapping. Yeah.
As I understood, pulsars and cosmology are the two main drivers of SKA. So I'm a bit surprised you are so happy about commensality. I would have thought that cosmologists wanted fully survey of their own. But if this is not the case, what would be the single project you would like to put most effort for SKA1 out of all this?
Probably the intensity mapping survey. Yeah, I think it's going to be the most. Yeah. Because the other two for SKA1 are going to be very similar to other experiments, like for example Euclid. So it's going to be very interesting to check, to use SKA1 as a cross-check with Euclid or this or any other. But the big improvement is going to arrive with SK2. But however, in intensity mapping, we are going to do something new. So intensity mapping, I think, for me, should be the priority in the case of cosmology.
Si te pasas del tiempo no te voy a decir nada, o sea que pues, como tú lo veas mejor. Si quieres cuestiones, quédate en 15 minutos y si no quieres mucho.
Cuando el día avisas, han pasado 15.
15.
Sí.
The next speaker is Guillén Anglada from the Instituto de Astrofísica de Andalucía, and he will talk about star and planet formation with the SKA.
About the prospects on the field of star and planet formation that are expected from the SKA results. I will talk in my own name, but this work has contributions for several people from the White Spanish Book, and in particular on the jets from Luis Rodriguez and Carlos Carrasco from the National University of Mexico. The topic I will talk on is inside the Cradle of Life SKA working group. But I will not talk about all the topics of this working group. In particular, I will not talk about prebiotic molecules, the onset of life, and I will not talk on SETI, which are two of the main topics of this group. I will focus on the physics, the chemistry, and this biology, sociology, and many things. So I will talk about the star and planet formation process, in particular on the development of high-velocity jets and the protoplanetary disks, which are the precursors of the planetary systems. The star-forming process can be simplified in this cartoon. a molecular cloud, a giant molecular cloud, is a very big structure with millions of times the solar mass, fragments into smaller cores. These cores collapse because of the gravitational force, and they form a central object, which is called the protostar, and at the same time, because of the rotation of the cloud, some of this material starts to rotate around the star, forming a disk which is made of gas and dust. This disk is a reservoir of material, and this material, part of this material falls toward the star, building the star, and part of this material is ejected because of centrifugal, magnetocentrifugal forces, and forms what is called a jet. And this system of the disk and the jet is present in almost all the phases of the star forming process. The final process is that the final situation is that we end with a central star which has most of the mass. Part of this material is ejected again to the interstellar medium in the jet, and the remaining gas orbits around the star, forming the exoplanetary system. So this system of the disk and a jet is present in all the stages, and is present, this is recent results, in all kinds of stars, from the very low mass stars, even the proto-brown dwarfs, to the most massive stars in the universe. Probably not the very most massive, but until the very most massive one, until 10, 20 solar masses, the same process works. And this jet that can be seen at very different wavelengths, here is an example in the optical, for example, is partially ionized. And this partially ionized material emits in the radio, emits free emission, is what we call a radio jet. The radio jet traces the material closest to the protostar. Here is an example. This is 0.2 parsecs, and this is the region of a few hundred AUs, which traces the protostar, which usually is hidden at optical and infrared wavelengths. So these radio jets are extremely useful to pinpoint the precise position of the embedded protostars, which are in very extincted regions. These are two examples. This is a very massive object with a very collimated jet, radio jet, and the central disk, which is traced by the dust emission with ALMA in this case. Here is another example of a low mass protostar. Here the jet is traced by the molecule of carbon monoxide, and the disk is traced again by the dust continuum observed with an interferometer. So the system of jets and disks are present in all the phases of the star formation and in all kinds of objects over the whole stellar mass spectrum. Because the radio continuum emission is not produced by the UV photons of the star, unlike the H2 regions where the emission is produced because of the UV photons of the star that photoionize the material and produce the H2 region. Here the emission is produced by the shocks in the jet itself, by internal shocks. So because these shocks are related with the process of accretion, actually there is a relationship between the radio continuum emission and the accretion, which in its turn traces the volumetric luminosity of the object. So in the log-log scale, there is a linear relationship between the luminosity of the objects and the radio continuum. So this is very useful, for example, to predict which is the spectral emission that we will have for the different kinds of objects, from the very luminous ones, then to the 6 solar luminosities, to the proto-brown dwarfs with luminosities of 1/10 of the solar luminosity. You know, this is what is expected from an H2 region, from photoionism mechanism, and this is very different, this correlation. So they trace different things. Even when the mechanism of emission is free, the origin is very different, and they can be used to trace the population of embedded protostars of all the masses, because we know and we can predict because of this relationship. Another aspect in which the SKA kilometer array can be crucial is in detecting radio recombination lines in the jets. So far, radio recombination lines have been detected only in H2 regions, but not in these jets which are much weaker than the H2 region. Just in a couple of cases, and one of these is by Isaskun, there is some amplification, major amplification of the emission, and there is a tentative detection of radio recombination line. But in general, these are not detected because we found this relationship between the continuum and the recombination line, and this is a very small number with very small flux densities. And detecting radio recombination line, we allow to measure the radial velocity of the jets, and using this in combination with proper motions of the radio continuum, we can trace the full 3D kinematic of jets. Another interesting thing is the recent discovery of non-thermal emission in these jets. The jets have the core that contains thermal free emission, but in some cases, the shocks produce non-thermal synchrotron emission, making the jets an analog of the extragalactic jets. The difference is that in the young stellar orbit jets, because they also have thermal emission, we can obtain the physical properties of the jets in addition to the magnetic field, which is given by the non-thermal emission. So we can try to make some kind of general model that encloses all kinds of astrophysical jets, both the low mass star jets and also the very big extragalactic jets on much smaller scales of several orders of magnitude more. So what are the prospects for SKA in regarding the jets? The expected sensitivity of the square kilometer array in phase 1 is about 1 microjansky per beam in 1 hour of integration time. It goes as the square of the time. So if you want to decrease the sensitivity by a factor of 2, you need to increase your observing time by a factor of 4. Okay? And so what can we do? For example, with the prediction of the expected flux density, in SK1 we can detect all the embedded brown dwarfs up to a distance of 500 parsecs from the Sun, just with 20 minutes of observation time per field. We can detect all the massive protostars in the galaxy with integration times of the order of 20 minutes. We can make high-resolution studies of the jets, trying to see the region very close to the place where the acceleration and the ejection of the jet is produced, and trace the physical properties of the jet along this. And this can be related with the extragalactic jets, where we do not have this kind of emission and we cannot obtain this precise information on the ejection mechanism. In the first stage, only the strong jets could be observed. We will wait to the full SKA to be able to study the full population of jets. The 3D kinematic of jets can be traced with radio recombination lines. This is something new. And even because lines can be stacking, and these things can be doing in times of just 5 minutes. The magnetic field of the jets can be also mapped in these non-thermal jets, and this can be related with the astrophysical jets of all kinds. The second aspect that can be where SKA can obtain results is in the study of the protoplanetary disks. These disks are made of gas and dust. I will not talk about the molecular gas, where there is a very interesting field in the study of prebiotic molecules. I will talk about the dust. This is the typical spectrum of a young stellar object. There is a lot of emission of the dust at short wavelengths, millimeter and the far infrared, and the free emission of the jet dominates at centimeter wavelength. So around 1 centimeter, these two mechanisms become comparable. So why is it interesting to study the centimeter regime where the emission is much smaller, much weaker? Well, this is because the process of planetary formation implies that the dust grains that in the stellar medium have microscopic size of a fraction of a micron, they stick together in the accretion disk and they start to building bigger objects. We expect that they will build objects of the size of several centimeters, pebbles, and then these will become planetesimals, and finally these will become planets. So all the stages of this process can be observed. This is, for example, an ALMA image. And one thing is that the biggest grains are expected to accumulate in regions that are called dust traps. And these traps that have that are observed, for example, with ALMA, is where the biggest grains are present. And the biggest grains are observed preferentially with longer wavelengths. A kind of rule of thumb is that if you want to observe a grain that has a size of 1 millimeter, you have to observe a 1 millimeter wavelength. If you want to observe a dust grain that has a size of 1 micron, you have to observe a 1 micron. So if you want to observe something that is 10 centimeters big, in principle the emission is stronger at wavelengths of around 10 centimeters. That is where this SKA should work. See, I do not know why this moved here. So this is the emissivity, of the grains. So red are grains of 1 micron, blue are grains of 1 meter, 10 centimeters. So at short wavelengths, this emission dominates, but here is some kind of scissors plot, and here the small grains at centimeter emission, the emission is lower than the other one. The price you should pay is that all the emission decreases. So in principle, it's easier to detect the disks here. Here there is usually not very much good resolution of far infrared, but the millimeter with ALMA, you can observe very well the disk. So why is it interesting to go here where the emission is weaker? For two reasons, because this emission is dominated by the largest grains, so you can differentiate better these two emissions, and most important, because this emission is optically thin here. In ALMA, the emission is optically thick, so you cannot see inside. You see everything with the same brightness. So if you want to trace, for example, we have done here, how is the size of the grains change with the distance to the star, how this process of grain growth is produced, you need optically thin transitions. The closest we can do now is to use the longest wavelength of ALMA, 3 millimeters, and the shortest wavelength of the VLA, 7 millimeters. This result was obtained in this way. If you use the shortest wavelengths of ALMA, you got nothing, because you cannot differentiate optically thick region from large grains. With the square kilometer array, this should be improved very much, because this map with relatively poor sensitivity could be obtained with much better sensitivity. Here is another example. This is the very well-known AGL tau map obtained with ALMA. But ALMA cannot see details of this because everything is optically thick. Everything has the same brightness. If you move to the VLA at 7 centimeters, you see that this is made of small clumps, and this is supposed to be the embryos of the future planets. Finally, another example is the photoevaporation of the disk. The gas in the disk is supposed to be removed by photoevaporation, by the UV photons of the star, and this can be also observed with the VLA and probably with the square kilometer array very easily. And finally, the detection of Kuiper-Bell analogs in other exoplanetary systems, which are made of big grains, is also another possibility for the high sensitivity of the square kilometer array. So here is a summary regarding of this, of what is expected to be able to produce the square kilometer array, the study of grain growth with optically thin emission, the imaging of the photoevaporation disk. This should be done with a very small amount of time, and the possible detection of Kuiper-Bell analogs in extrasolar planetary systems. Thank you.
Any question?
Thank you. If you were to include magnetic fields in the star formation process, would there be any consequences, for example, for the jets? And would you be able to constrain maybe the primordial magnetic fields? I mean,
well, in the case of jets, thermal emission, it is possible to map the magnetic field in the jet. This is the polarization vector of the synchrotron emission, and this is the direction of the magnetic field. In this case, for example, is very well aligned with the jet. The magnetic field, for example, in the disk, can be traced through the polarization of the dust. Okay? And also, in this case in particular, we did recently a study with ALMA of the polarization in the disk, which has a combination of scattering and the effect of the magnetic field. And also, in the past, it was made some map of the distribution of the magnetic field in the cloud around this object. For example, this is interesting because this is very well aligned with the disk, and the magnetic field in the jets is random, and outside the jet, I mean. And also through some molecules, for example, the water molecule, with the major emission of the water molecules, also can be measured the magnetic field. So it can be measured at different scales and in different objects.
so in the star formation model, you're including the magnetic fields?
Yes, the modelings usually include the magnetic field. They assume that the clouds, well, there are different theories because there are people that say everything can be done with just turbulence. But for example, you can think of a cloud which is magnetically supported, and then because of magnetic diffusion of the magnetic field, the magnetic support is lost, and then the cloud starts to collapse. Okay, and in the ejection of the jets is absolutely necessary the magnetic field, because otherwise you need a non-conservative field to be able to transform the velocity of the material which is in falling here and move this in this direction. And this is the way the system loses the angular momentum, because otherwise it will not be possible to make a star, because the star will rotate too fast and will be dispersed.
just quick comment. The physical scale, how far can this jet extend?
Can extend even in low mass stars for several parsecs. For example, this one, I think it extends around 5 kiloparsecs. What? Here. Sorry. Well, this is just the core. This is 1 parsec, okay? But it extends for several kiloparsecs. So it means that if a star forming close to our sun, we probably receive ejections of the material, the remaining material of the closest star to our sun, because the scales they cross are of the order of the separation between the stars, of several parsecs.
In order to produce all these heavy hard objects, you need to, of course, claim a lot of info of material, and that's the reason for this of water, and that are because of these vapors that are produced as consequence of the continuous form of bodies. Can you do you know about chemical gradients that are talking about these inferences because of the continuous inflow of materials in the protostars?
Well, chemistry is not my topic, but there are chemical abundance gradients from one region of star formation to another. There are inside the same core, and there are inside the protoplanetary disks. And it is a combination of chemistry and physics also, because one concept that is called the snow line. So in a protoplanetary disk, the region closest to the star is hotter, and the region at larger distance is colder. So at the long distance, the molecules are frozen onto the dust grains. They have a shell surrounding the grain where many molecules are frozen, and even some molecules are trapped there. So until the water, for example, is not evaporated, they cannot be released, and then we cannot see them. And each molecule has a different sublimation temperature, so there is the CO snow line, the water snow line, and for example, you want to build a gaseous planet like Jupiter, you need in principle to build it at long radius, because in the inner region you expect this material to be evaporated, okay? But then planets can migrate and everything. So it's very complex, the chemistry, and this is a very interesting topic, of course.
Let's then thank the speaker.
So the idea that we had for this the first set of talks was that maybe some of the questions were going to be solved in the next talk, in the first set of 4 or 5. So we thought that maybe it was better to gather questions in one round of table, but I think that some of the questions may be answered by other people in the audience. I just tried to have a kind of representation of different kind of questions. I think the only person you didn't know yet is Anna Bonardi, who is a project scientist at the SKA, so she's in close contact with the science working groups, because you know Immaculada and Phil. So everything you want to know about, I don't know, about the participation in things or whatever. If you don't have questions, we just go for lunch, don't worry. But, well, your turn. Pablo.
Comments on surveys of use of the SKA for batch. To be able to use the SKA in different observing modes at the same time, and I can, for example, think about a pulsar mode and at the same time the imaging mode. Hello, now? The SKA probably, I mean, we want to use it with different observing modes. It's planned to have this mode and be able to observe different observing modes at the same time.
Yes, okay, I get that. There are some observing modes that can proceed in parallel, and the example that you give is correct. So, for example, the pulsar search. The pulsar search is going to operate during other observations. This is also possible because it has a separate processing engine, which can therefore not interfere, for example, is sort of detached almost completely from the imaging processing. There are other things that can be done in the same way. For example, due to the fact that the STP is also a buffer, you can have, so you don't have to analyze everything in real time. You can have more than one processing done on a single field. If you need, for example, a different spectral or spatial resolution, you can have a first batch of processing in one way, and then you could park for a little while your data and reprocess. So you could also potentially have some different imaging specifications, but of course this is a bit more constrained because you cannot really build up more observations that you can analyze. But there is some room for that, and of course the role of the regional centers that has been said already this morning is very important, because once a single scheduling block has been processed into the standard product, then there are multiple of these advanced data products that can be delivered from that. So this will give the possibility to create from this initial set of standard product a much wider group of final user products, advanced data products for scientific use.
Data we aim to produce. I wonder, will this data product be, will they be distributed to all the science regional centers, or the PI has to choose maybe a couple of them where this data is going to be moved, and how is this going to be attacked?
The regional centers will be this federated group of centers, and it will be completely irrelevant to the users where exactly the data is analyzed. So it is possible that, for example, some of the centers will have typically an hardware more suitable for some processing and some other with a different processing. So there will be a layer that will make it completely disparate. The user will assess the outer layer. So, for example, they will want to download the data from this node, but where this is processing could be completely detached. and optimized, let's say, for the computational efficiency, for example, or for the specific expertise that's needed in some processing, which could also be a bit different between different nodes.
I have a general question. At the moment, the whole science working groups basically is completely open, so the access, basically anybody who has some interest basically can join. And I was wondering when there's going to be a more formal process, and how it's going to be with the data access in general. What is going to be the policy with that? I mean, who's going to have access to the data, and for how long? Will it be only part of the organization? Or so basically my key question is when it is going to be more formal, the whole structure.
You're quite right that at this point that policy has not been worked out, but it is one of the high-level aspects of that is one of the key policies that need to be agreed at almost the first meeting of the SKA Observatory Council, that is the governing body of the new treaty organisation, which we expect to happen in about June of next year. But I can give you a view on what that might look like, but don't write this down and come back in 2 years' time and say, you said this, because it could change. But a view is that, and I did show a pie chart which indicated that access to the telescope time will be through a peer-reviewed science process to all scientists based in the countries that are contributing to construction and operations for the SKA. There will be a small fraction of time that is available for what we call international time. That is for countries that are not part, just in case there are superb science projects which are proposed by countries outside of the membership. So this is a move away from the traditional radio astronomy open skies model, which is unfortunate, but reflects the fact that the cost of SKA is such that it dwarfs previous investments in radio astronomy infrastructure. So that is the process that is being developed. The intent is that we will have a single time allocation committee. So we are able to select the best science that comes from the partners. And then but over a period of years, the partners and the governments are telling us that in general, they would expect to see teams led by or with a majority of members from their countries would get time more or less proportional to the contribution that they are making. But they're not going to insist on that from semester to semester. It's something that we will look back over a period of years and judge whether that has been effective. And if not, some arrangement might have to be made if one particular country is disadvantaged. It's a fairly complex thing to work out because we expect with the big key science projects, they're going to be massive multinational teams. So exactly how one works it out is, we thought a little bit about, but all we've decided is it's hard, it's complex. So we'll see how this area develops.
And what would be the policy for the data that precursors are already taking, like Meerkat, for example? Is that affected also by the SKA organization, or it's different?
No, it's the organizations that are building them, and they have their own data policies. And I know it's the Australian precursors are fully open. They have an open skies policy. Meerkat is going that way, although I think in the early stages they are favouring South African-led projects just because of the amount of money the South African government has put in. But ultimately, you know, they are broadly an international, looking at the international community. But no, we the SKA Observatory, SKA organisation, have no influence over the policies of the precursors.
Thank you. Just a couple of one suggestion and one question. The suggestion is, since there are not many people from the industry besides the CDTI, which is here, I think it would be good that at the time of the procurement not to make very big packages like was done for the ELT, which I think we are now paying the consequences of this high risk, which implies having these big packages which only one company or two can afford. And I know that that's a problem in terms of management, but I think in this very, game changer, to use the same term, kind of project, it will be risky to have everything in hands of one single company that have to do the whole thing. So it's just a suggestion based on what we have seen with ELT. And the other one is a question, it's a delicate question, but it's how does the funding of SKA is protected against the effects of Brexit?
As we become the SKA Observatory, we will be like ESO. Let's take that as the simplest example. And so as a treaty organisation, although we're headquartered in the UK, we will sit aside from the local national politics. So the funding, let's say the UK funding, because that's the one specifically that might be impacted by Brexit, I am assured categorically by the UK Minister of Science and by a whole range of senior officials that the UK has made its funding commitment and intends to abide by it. So I'm reassured by that. I don't think there's going to be any risk at all. The only potential impact of Brexit is, or the most significant, I think, is the length of time it is going to take the treaty to be ratified as it goes through the British Parliament, because the British members of Parliament are somewhat distracted at this moment. So that I think is the one thing that I watch carefully.
My question is more about the Aeneas project, which is, I think, is this kind of consortium in Europe to start building up the regional centers, or this federation of regional centers. Is that correct?
The European Federated Regional Center.
What is the current model, or is there any kind of idea at the moment on how that is going to be distributed, or what countries are going to be hosting these regional centers, or is that something that's been at the moment discussed, or what is the stage?
Let's say pronounce itself on the governance regional centers, because this depends much on the, I understand, if you can correct me, more on the agreement or the conversations between the SKA Council in the future and the steering committee who is working on that. The role of Aeneas, and it has different working packages, is more about proposing. It has areas about the data, sharing the data, the computational resources, mapping the resources in Europe and how to integrate them, following standards, etc. It's true that we are working on a governance model. The result of this is going to be discussed in 2 weeks from now during the AWARD. There is a special meeting about that. But in any case, this is not going to be binding. This is going to be just a proposal for how this should be done. And maybe Susana, because Susana is very active in Aeneas, so maybe you can mention.
What you say, the model In AENEAS, we are trying to provide a design a design of a federated network of nodes that are distributed around Europe in order to provide the resources and the tools and access to the data. It's not related with governance. And now at the end, AENEAS, it will end this year, and in this year we are trying also to see how the European Open Science Cloud how can we integrate these new tools that come from this European Open Science Cloud can improve or can be integrated in this federated network of nodes.
This question may be a little premature, but are you considering doing an all SKA or an all Southern SKA survey early or late in the life of a SKA? Because, it's a lot of time, but it gives a lot of presence to the instrument in the world. Or you haven't really thought about this?
There is the sort of World Visible Sky survey envisaged. It is part of the key science projects because, as you say, it will accumulate a lot of observing hours. Although it is true that this will be a very important legacy, so, in principle, the sooner the better. We also believe it's very important that the instrument and the processing is very well understood before you start an observation like this. So our program at the moment is to start first, possibly with maybe the first couple of years, focusing more on shorter PI-led projects that will help us to understand very well and improve and very stable all the processing, understand well all the systematics, and then move on to this very deep integration, because in this those kind of systematics and error in the processing, given the very big number of hours, will become limiting factors. So we need to make sure that everything is done correctly and we don't hit a sort of noise due to the fact that we don't calibrate very well and things like that. So we should start this couple of years into standard operations.
If I may add to this, I think it's also very important the concept of commensality, so that in order to optimize the use of time because of the many different instrumental configurations, what is going on now in the community is trying to create working groups between the different science working groups who work on commensal science, so that if you design a survey, not a full SKA survey, but at least a large area survey, this is useful for different science cases. And this is a way to optimize the time. So there is a lot of work on commensality now.
Yes, I was late this morning, sorry, and maybe I missed some information, but my question is related to the previous question, in the sense that I wonder what is the elapsed time between the observation and delivering data, processed data and maps for the users to be analyzed and to get scientific results. What is the elapsed time? I suppose that this depends also on the kind of observation, because if you are looking for something in cosmology, you have to wait until a sufficiently large part of the sky is covered, right? But since, as you mentioned, there are issues related to systematics, etc., do you have an idea of how long it will take to solve all these issues?
Worked out answer to that. This is in the domain of the regional centers, And there is for sure, so we are not, I think the sure is that we are not going to wait until we've collected all the 1,000 hours before getting into, to the people, to validate and work with. And this is also because, especially for these long projects, we also foresee some sort of review of how the survey is going and whether it is going to meet let's say, the requirements and working. So I think the model could be that, the heavy lifting calibration is done as the SDP, and this is sort of regularly, as soon as possible, sent to regional centers. And the regional centers will then do their part of the processing and be the contact center for also the group, and, possibly develop some cadence in which this is done. I don't think this is worked out at the moment. No. No.
Could I add to that? I mean, in cases with, I think, with big key science project teams, we would expect those members to be integrated, to be the ones evaluating the quality of the data when it's delivered to the regional centres, to be fully integrated into that process. So I think the members of those teams will get access to the data almost immediately and be feeding back quality information, I think, to the SKA Observatory. But as Anna said, we haven't worked out all of the details of how this might work yet. As the regional centre model, as the thinking around that model grows, these are the sorts of things we will come across. And I should say we're having a meeting. Over the last few years, as well as the science meetings, we've had a regular series of engineering meetings for the SKA. But because we're coming to the end of the detailed design phase, this year in November, hosted by our colleagues in China, so it'll be in Shanghai, we're having a meeting which has part of the focus on engineering, but also what we're hoping is to get a lot of people there for a first public discussion about the commissioning, the operations, and regional centres. So we want a lot of community input as we develop those plans. And this meeting in November will be the first real opportunity for the community at large to come and give us that input. So we'll have various presentations, and there's documents being developed which will provide our thinking on this, but we very much want the community input as well.
I can add to that, in particular, as part of the Regional Centre Steering Committee, myself, together with Andrea Posanti and Rosie Bolton, we are in charge of finding all the possible channels to get feedback from the community in order to make sure that whatever the result on the way to organize the regional center is useful for the community. And from my personal point of view, there is not such a thing as a regional center in the community, because at the end, I think that we are going to build on top of the efforts to exploit the data of the precursors and pathfinders, and probably I think many of these pipelines are going to be implemented, expanded or modified to reduce data and to get advanced data products at the regional centers. And that's why Susanna mentioned that open science is important, because I think at the end we are the community, and there is not going to be, I mean, a regional center is not a computational center. The computation is just the tool to analyze data, but you need the tools, you need the archive, you need a lot of things. And all these things have to come from the community at the end. So whatever the level, the international level or the national level, I think this is not separate. This is all together, coming from the input or the implementations or the software or the expertise of the community. That's my point of view for that.
I think what you just said motivates me another question, which is if I understand correctly, there will be several regional centers all over the world, and then the question is the idea that each regional center will do all the processing, or is a repartition of different tasks? And how about redundancy, or is, because probably you expect that several independent groups try to do the same in order to cross-check if the result is fine. All this is...
Some of these, and I think all this is on definition, like how many copies of the data will be and where they are going to be. I think all this is going to be very much coupled with the distribution of the community that's going to use the data or that is going to provide tools. And I think, I don't know if this is the idea, no?
Yes. In general, it is big volumes of data, so we don't think it will be efficient that, for example, every regional center have a copy of everything. Mm-hmm. So if there isn't the need to do such a thing, and at the same level, extreme redundancy also I don't think is very efficient. I think the idea could have to have more than one pipeline, for example, especially in those cases when we need to test that everything is good, especially, I would say maybe more at the beginning. Maybe have the opportunity to test some newer method with other methods. But I think ideally, ultimately, what might happen is that due to hardware consideration, expertise and pipelines, you might decide to send some processing here or there, depending on where it is more efficiently processed. And then if this needs to be assessed somewhere else or in multiple spots, there will be this mirroring, essentially. So regardless of where it was the main place that was efficient for your data to be analyzed, you will be able to access at your local node, for example.
Yeah, I think a sentence I liked very much from the regional center steering committee is that whatever the solution is to optimize science. It's not about politics. So I think that's very, very good and relevant.
Inmaculada, I was wondering if Spain is member of any other scientific facility in South Africa and Australia, and in this sense, if there is some experience in supporting these scientific collaborations, considering, for example, the distance and how these are kind of special in a way.
Of any other scientific collaboration with sites in Australia and South Africa. So this is the only one that, so I can tell you that we are part of many of these big international organizations that mentioned this morning Rafael Rodrigo, but none of them is having sites in both continents.
Relevant for the audience. Do you think that there is room for kind of support for this kind of collaborations? Because I mean the working in this kind of projects requires additional funding. For example, there are additional needs compared to others, and
endeavor in which all the community, all the countries are involved. It's a big investment. We're in the phase one, and this is, as the field was telling us, it's around 890 or something. Mm-hmm. This is the investment that is expected could be necessary. Spain, of course, is involved in many other big infrastructures, as you mentioned, and as it was mentioned this morning, we are part of the European Spallation Source. It's an infrastructure that in which the cap budget is 1.8 billion euros. Of course, the big one, CERN, ISO. So I think that it is going to be in SKA for the ministry. It is important because we consider that it's one of the biggest projects for the future. We are convinced that it is good for Spain to be there, and this is the reason why we are here, and we are joining this organization since 2011, I think so. I have been there, sitting in the second line of the table, with the intention to find the best moment in which Spain could join definitely the organization. We did a good step in last year, joining the SKA, and as mentioned this morning by the Secretary General, our intention, and we have had the opportunity to discuss also with Phil, our intention is to progress and to work together in order to go for this, for joining this international convention, this international organization, and to be one of the next signatories of the convention. We are going to work on that. This, of course, is related with the availability of funds, related with the policies and the strategies of the country. I think that the new government is going to be here soon, very soon, and we don't expect big changes. So we have all the expectation that we will proceed with the steps to try to join. It's better sooner than later.
Always been there more or less since 2011, even before. So, and you have always been very supportive. So I would like to thank you for that.
Yeah, I want to also to ask about this funding, because indeed I think one of the mistakes from Spain has been that we have been entering some very big collaborations, ISO, other, and I think specific funding to support groups, or actually to prepare, to exploit those huge amounts of data had not been to the level at the time. So the usual national plans is the way to get funding for this, and I think SKA, we should not repeat, in my opinion, the same mistake. So that's one thing, just a comment. And then to prepare towards SKA, I think it would be useful to have to allow at least to have some collaborations, via ministry to ministry, Spain to South Africa, for example, to get with Mercat access. Italy has done this. Basically, it's just an agreement, no money, but basically allowing groups to ask for some funding. I think this would help us to get ready, for that. It's not much money; it's actually peanuts. So thanks.
The strategy that we probably will follow in the future is to that we couldn't do it because we haven't the resources to go ahead with this. We need all of you, because finally we are mobilized by you, by the scientists, and for the companies, for the private sector, in order to find these special contributions that are more valuable for Spain. It's true that the state plan is not the way, it's not the best way. When you decide to go for this big collaboration, you can't take this decision in base of the competitive calls in the state plan. So the intention is to open lines in the national budget in order to have the money available for joining this kind of organization. And of course, it is very important, as you mentioned, that the support is not only for paying the contribution, because if we pay the contribution and we don't do anything here in Spain in order to give money for the institutions that are going to participate and need this money in order to get this level of contribution, it's not possible to join. There is no sense for joining in this way. So it's clear, and also was mentioned this morning by the Secretary General, that our intention already in the budget for 2019 that finally was not approved is open special lines in the budget, not going through the calls of the state budget, to support coordination at national level also of the collaboration, of the national participation in per kilometer rate. We are convinced of that. We need to do it, but of course we have to take into consideration the availability of resources for doing that. But of course this is in the mind of the ministry to proceed this way. not only for SKA but for other projects that in the past was based on the calls of the state agency.
Okay, looks like a good way to finish the roundtable. We can continue anyways in the patio with lunch. So thank you everybody for